I gave you those, didn't I?
I wasn't here. No.
All right, one thing real quick. If you miss a day, you come see me before you start complaining about anything. So, with that said, who else still needs this here? The handouts? Anna, I think you need it, right?
I know you miss me.
I think you missed me. I just gave you
Yes,
the
I did.
minute. Yeah.
I did, actually.
Bonnie.
Oh no, I was actually kidding. I was here when we got them. That was my sarcastic moment.
All right.
And then
You got a pissed off moment from me, so I'll calm down. So real quick, on this, an extra added feature on this is in blue are quizzes. You can see there's a quiz 7.2 through 7.5 on next Wednesday. What's happening Monday? Holiday. I love it. Wherever, whatever destination you want. It's up to you. All right. Whew. No, not really. Not necessarily. Okay. So just to get back into what we were doing last time.
7-2-1?
Just to do a clean sheet here. So last time we were talking about the conversions, and that was this handout here. We were talking about, oh yeah, maybe just the one that says whiteboard. So at the top you see how to convert from polar to rectangular and vice versa. And as you go through your math, if anybody's going to go much further in mathematics, you're actually going to find out that there are, in one sense, an infinite number of coordinate systems. In a better sense, there's not an infinite number. There's just slight variations on a smaller family of them. So you have rectangular, you have polar, you can have spherical, you can have cylindrical, you can have all kinds of, there's like, I don't know, 20 some odd that I've worked with throughout my career, but most of the other ones are just slight variations. So obviously if you're working with like spheres and you want to find volumes of spheres, you probably want to use what's called spherical coordinates. They would but if I'm working with rectangular boxes, then I want to stick with rectangular coordinates, x, y, z, three-dimensional. So it depends on what the problem is as to which set of coordinates you're going to use. So we're expanding our knowledge of coordinates by one. One more coordinate system. See, I figured out last time we used was. Oh. So last time we did this, I got a clean one here because the other one got a little bit messy.
You can't see that. Brighter? Brighter.
Whoa.
Whoa.
You got a bonus zoom. All right. So this was just an exercise, and in getting used to how to plot points. Now, back a million years ago when you first learned how to graph points, who remembers what you did immediately after learning how to just graph individual points? Connect them with lines, but those lines had associated equations. So our next step after doing this kind of thing is going to be plotting full out polar equations. Oh yeah. All right, seeing what they look like.
Do they have like distance function?
They'll have, not that we'll necessarily talk about it, but they'll have like ideas of symmetry we'll talk about, just like we have symmetry in, even and odd symmetry in rectangular. We have ideas of symmetry in polar. They'll have ways to find distances between things, certainly, and that'll have to look different because our distance formula is based on x squared plus y squared equals distance squared, right? So it's going to possibly have to change here to be in terms of polar. Will we talk about that? Maybe. So a lot of what we do in rectangular, we have to kind of refigure out how to do it in this coordinate system. And it's really, you would only do something in a specific coordinate system if that's the easiest one to do it in. So obviously, if I want to graph something circular, I would probably want to use polar. Those equations can get kind of ugly in 2D. Imagine in 3D what the equations would be for some sphere with x, y, and z. It's not the grossest thing in the world, but it's a lot simpler in spherical coordinates, in 3D polar. So the basic idea here, just on graphing these points, and the idea of scale here is a little bit different. Because instead of tick marks, we now have these circles. And those circles denote a scale on what? But the tick marks on the y-axis obviously denote the scale on y. What do these circles represent? R. Right, so if I want to go R equals 3, I'd go out 3 places, and I get to pick my scale. Very often, if I have an equation like cosine of 2 theta, and we're going to plot that, I actually would probably want to make my R equal to 1 be way the hell out here. Maybe way out here so I can get all kinds of resolution in the middle. So when I'm trying to plot 0.213, I could be just a little bit more precise. Believe it or not, I've had people tell me R is 1 here and then try to draw something in. There you go, Jeff. The hell is that? So give yourself a little more space. Pick a good scale. It's the same issue with x and y. Sometimes we have trouble picking our scale. Same thing here. So I think last time we picked 1, 2, 3, 4. Every 4 would be 1. So we have like R equal 0.25, 0.5, 0.75, and then 1. And so forth. All right? So that's 1. 1, 2, 3, 4 would be 2. And so forth. That's exciting.
So don't get overly excited. Don't go for like the big one. Just kind of like figure it out first.
Say again?
Like not necessarily go for the big circle first. Just try to figure it out before you start to draw it. Or how do you figure it out? Like,
So we're not quite to the point yet where we can plot equations.
oh, okay. So.
But because you'll have to think about your scale when you find your equation. And with cosine and sine, it's all got to do with the amplitude, right? If the amplitude is 5, if they have like 5 cosine of 2 theta, what do I want my R out here to be? 5. So then I got some room in the middle to do all my other points. You with me?
Yeah.
I don't want to make my scale 1 because then 5 is going to be way the hell out here. And then you got to stand on your graph paper, and I don't want you to turn that in. Giant piece of paper. Here you go, Jeff. So let's not do that. So let's try to graph this last dude here. Why not? We'll start from the end. So 11 pi over 12. And this is one reason why I like this graph paper. When you look up polar graph paper, when you Google it, I don't know if anybody's tried to do this yet, but if you go to Google Images and Google polar graph paper, you've got all these options that you can print out for yourself. This one is the one that gives me a lot of information without like packing it with too much shit. Right? You see both. You see totally blank, or you see packed with too much crap. This is pretty decent scale here. It goes a lot deeper than we did before. We never went to 12ths of a pi, so this is pretty good. So here's 11 pi over 12 here. Right, so there's my angle. So if anybody wasn't here last time, you're freaking out. Right, I understand. So we have the option, I can tell somebody how to get to a point, this point here, by going this far out, that's X, and this far over, that's Y, right? Without stepping on it. Or I could say, how do I get to that point there? Turn by a certain angle and walk out this far, and then you're at that point. So that's what these points represent. Turn by this angle. All right, cool, so I turn by that angle. So I'm facing this way. But now, what is it about how far I've got to walk? Back to, exactly. So that negative on the R means walk back to. So here I'm going to walk, where's my 11 pi over 12? There it is. So back to 1, 2. That's F. Is that cool? Do you guys see that?
Oh, but because you made your scale, okay.
Yeah, so here's 1. Here's 2. 1, 2, 3. Here would be 3. So you need that here in a second.
Okay.
All right, how are we doing so far? Is that right? Okay, okay. So then maybe to do this one here, first I turn where? Negative 2 pi over 3, right? So that means here's 2 pi over 3. And so I want to actually be facing this way. Here's negative 2 pi over 3. So I'm facing, here's 2 pi over 3, so I'm facing this way. Let me see if we can keep it straight. You do it just there. I'm facing this way, are you guys with me? There's negative 2 pi over 3. And I want to go, how far? Oh, back 3, right? So actually I want to go that way. So what's another way to say this point that's a little bit easier?
3,
Yeah.
2 pi over.
I could just say 3, 2 pi over 3. They're actually the same exact point. Don't think of it as negatives cancel. It's just, you actually can make that a general rule, but those both land at the same place. So I can tell somebody to turn a certain amount and walk backwards, or I can tell somebody to turn, let me do this again. So I can tell somebody to turn negative 2 pi over 3, that would be about right there, and then walk backwards. Right? Or I can tell somebody, oh, I've done that completely wrong.
Isn't too good?
I'm doing this. All right. Let me just back up. I'm trying to make it a little too easy. So if this is 2 pi over 3, where's negative 2 pi over 3? Down here.
Yeah,
That's my
okay.
fault. Thanks. Go ahead and tell me that. I'm trying to do up here and over here. I'll make stupid mistakes. So here's 2 pi over 3. So negative 2 pi over 3 would be, and you can label these for yourself. Like here's 7 pi over 6. Right, 5 pi. And that's, here's 7 pi over 6. 11 pi over 12.
Okay,
12
what
pi over
happened?
12. 13 pi over 12.
We can see.
Oh yeah, when my hand gets in there, it gets really bright. You guys see my little bit? So negative 2 pi over 3 should be over here. And it should be the same distance away, so it's like 1, 2, 3, 4. 1, 2, 3. So here's negative 2 pi over 3. Back there. All right, doing all right? All right. That's it. Yeah. So what kind of told me I was on the wrong path was when I was like, okay, what's got to happen for turning a point around?
Why is it 7, 6?
Where are we at here? So if that's 5 pi over 6, 6 pi over 6, 7 pi over 6. You can fill in some of these if you want to. They're blank.
Also,
You see, that's 5 pi over 6, 6 pi over 6, 7 pi over 6. Every couple is another pi over 6.
And it's
So that's
8
8 pi over 6, which is also
ridiculous.
4 pi over 3, which is the 2 pi over 3 reference angle that way. Not really reference angle, but still. Okay. So if I'm facing in this direction, I'm facing this direction, right? Negative 2 pi over 3. And I want to go back 3. That way. I like it. The way I want it to be related to a 180-degree turn if I wanted to turn it around. So the quicker way to say negative 2 pi over 3, face that way and go back 3 is to actually just say turn to pi over 3. Because that's 180 minus 2 pi over 3. You with me? What's 180 minus 2 pi over 3? I know I'm mixing degrees and radians. What's pi minus 2 pi over 3? Pi over 3. Yeah. Right, so instead of going this way, I can do the full 180 and go that way instead. So I want to face negative 2 pi over 3 and go back 3. What can I do instead? Face 180 away from there, pi over 3, and go forward 3. Okay, cool. See again? It's the same thing, yeah. So not 2 pi over 3, pi over 3. So if I face negative 2 pi over 3, here's negative 2 pi over 3. I face this way, but I go back 3. I'll end up here. So it's the same point. Negative 3, negative 2 pi over 3 is the same point as 3 pi over 3. Because these two have to be offset by 180 degrees. Cool. Okay. I'm still not used to this. Anyway. But do we get, let's try one more here. I think last time we stopped at C, if I remember correctly, so let's try to do D. D is going to be relatively easy now. How far do I want to turn? Pi over 3. And I want to go out 3 halves. So I want to go out 1.5, so it'll be 1.5, so right in the middle of these two. Somewhere there.
What? Are we doing D?
Yeah, D.
Oh, yeah.
So D, what D say? Turn by how much? Pi over 3. So turn by pi over 3. And then go out 3 halves, so 1.5. So there's D. And this in here was E. Okay. So the basic idea of plotting straight up points in polar is not that difficult. I'm hoping we see that. The one little thing to get used to, though, is the fact that you can have R be negative here. It makes sense. Just like you have X and Y be negative, here you can have R be negative, and it means more like just walk backwards. Okay, that we know support. So it doesn't truly mean your radius is negative. It just means for the angle you gave me, I have to go backwards to get where you want me to be. That's all that means. Okay. So the next level of this, and I've got another little clean one I can give you guys, is to graph full out polar equations.
This 8.2?
This is 8.2, yeah. So let me give you this. You got a little bit of room for work. You got a graph. That was 8.1. Basically, the handout I gave you last time, the one we were just working on, that covers all of 8.1. That's what 8.1 is. Oh, I'm sorry. I could put that somewhere else on. You need no? Another one, which one? Oh, okay. All right. What's up? Just
one more.
Alright, so let me see what's going to start with. I might actually.
Should it be focused on the screen?
Oh, don't worry about it. Yeah, we first need to do some work. So let's do this. Let's start semi-small. Why not?
Can't see it.
Don't worry. Oh, don't just hang out. Just wanted it right.
This is a 8.2 or 8.3? 8.2?
8-2.
Water?
Yeah.
Oh. Is this 8.2 or 8.3?
Say 2.
Oh, shoot.
8.1, like I just said, is covered by that handout. 8.1 gives you the conversions.
What? I'm so sorry.
8.1 gives you conversions both directions, and it makes you plot points in polar coordinates. That's 8.1. 8.2, we take the next logical step, which is the same step we take in algebra. Once you learn how to plot points in a coordinate system, you start looking at equations, using those coordinates, right? Okay. So here's our first little equation. R equals 3 cosine theta. And let's do this one 2 ways first, and then I'll show you why one way is a little better. Actually, let's do this the better way first. That might be good. We know how to graph cosine. What's the only real difference with this one? What's the amplitude on this guy? 3. Don't freak out. Here's part of the problem is this is not enough space. All right. So if I wanted to plot this, plot one full cycle. We've done enough of these, and this isn't even a very difficult problem at that, right? I mean, I could make this a lot worse, but this is fun. So I want to go 1, 2, 3, 1, 2, 3. What's the period going to be? 2 pi. Nothing's been changed with the period, so it's the natural 2 pi. So here's pi, pi over 2, 3 pi over 2. And let's get just a little more precise. Here's pi over 4, for example. What else do I want to do? That's enough to start with. So where does cosine start? Yeah, it's going to start up here at 3. Right, so cosine starts at its maximum as long as it hasn't been shifted somewhere. And then when's it going to hit 0? Pi over 2. At pi over 4, what is it?
1.
What's pi over 4? Cosine of pi over 4?
2 over 2.
Root 2 over 2. So in this case, it's going to be 3 root 2 over 2. So somebody help me out. Root 2 divided by 2 is roughly 0.7. 3 times that is 2.1. So it's going to be roughly at 2.1 at pi over 4. So that's a little more precise than we've gotten before. And then you just kind of continue at what happens at pi. So it starts maximum, goes 0, and then goes minimum, then goes back to 0, and then goes maximum. All right, cool. So this is basically what that looks like in this coordinate system here.
Why do you know it goes minimum? Oh, because the amplitude.
Should be the maximum. All right, so that's what that bad boy looks like. And that, that should be a problem. You're like, well, why didn't you give me that on the test, Jeff? Shouldn't be that big of a deal. Now, personally, I kind of like, so I'm going to do it the other way also. This is really just gives me a quick reference, because what I want to do is I want to plot these values in this form. So really all that does is, instead of being, this is still rectangular coordinates here. That's really what this is. These are x inputs, these are y outputs. So that's not where this should really live. That's not where this really is at home. It's going to be at home here. These are polar coordinates that has more to do directly with trig functions. All right, maybe. So just to be a little more precise for a second, let's just look at the first quadrant really before we go crazy. For input thetas and output r's, 0 of course is 3. We see that here. What about pi over 6? What's cosine of pi over 6? Root 3 over 2. So see what I'm doing down here is I'm making what we used to do like an XY table. When you first teach somebody how to graph lines, the very first thing you do is make an XY table, because that builds on the idea of plotting points. So we just learned how to plot points in polar coordinates. It'd be great to have just a collection of points to plot, because we know how to do that. And then you connect them with a line.
This is multiplied by 3.
Yeah, thank you. Times 3. Cool. I was going to throw that in there, and then I just started talking. The next good place to go would be pi over 4. We already did that up here. That would be 3 root 2 over 2. And then pi over 3. What's the cosine of 60? 1/2 times 3, so 3 halves. And then finally pi over 2 is where it goes to nothing. So I really only need the first quadrant to reference, because now in every other quadrant it's just going to change signs accordingly. Right? So you really only have to make an XY or a theta R table for the first quadrant, at least so far. So now if you look over here, and you guys have your collection of points there. So reference your collection of points as I do this. And you also have this picture, which is a quick visual to make sure that you're getting it right as you're plotting it down. Now here's where we got to be careful. At 0 degrees, so if I'm facing 0, which is really facing this way, I want to go out how far? 3. And in fact, what's the furthest that we're going to go out? 3. So it might be good to make a good big scale. So maybe go out 1, 2, 3, 4, 5 for 1. Right, so here's 1. And then, where am I at? 1, 2, 3, 4, 5. Here's 2. 1, 2, 3, 4, 5. Here's 3. Let me do this in a different color now. So those of you who like color pencils for graphing, you guys are awesome. I often say that I would hate to have me as a student in my class, because I'm sloppy and I don't show a lot of my work. You guys aren't going to do that, are you? Do what I say, not what I do. So at 0 degrees, it should be out at 3. So I'm right there. And then when I face pi over 6, how far am I going to go out? Yeah, and what's 3 root 3 over 2? If you do that, it's like 2.6 or something. Somebody help me out. What's 3 root 3 divided by 2? It's like 2.6. Or maybe it's 3 root 3 divided by 2. Okay, 2.6. This is roughly 2.6. Cool. So, how are we doing so far? Okay. So if you're facing pi over 6, you go out 2.6. And we've done this in terms of 5 for 1, so every 1 is 0.2. So here's pi over 6. Then I want to go out 1, 2. There's 2. 0.2, 0.4, 0.6. There's 2.6. How are we doing? Doing okay?
Can I see your point system here?
So here's 1. Here's 2. I just didn't want to draw a big circle and get in the way of my graph. And here's 3. So as I need it, I'm going to make a little line for myself to tell me where 2 is.
2.6?
2.6, right? That's what 3 root 3 over 2 came out to be 2.6 roughly. Okay. So obviously these do not have to be so very precise. We're doing it by hand. We can give ourselves, just go out to 1 decimal place. That's plenty. Okay, so then when we look at pi over 4, we want to go out to 3 root 2 over 2, and that's roughly 2.1. So at pi over 4, base pi over 4, and I want to go out 2.1. So 1, 2.1. That's why it's not a bad idea in general to try to have that scale where you can have 0.2, 0.4, 0.6, because then to find 0.1, 0.3, you just go in between. So this is 1, 2, 0.2 would be here, so 0.1 is right in between. How are we feeling so far? Are we doing okay? Okay. And then when you get to pi over 3, 3 halves, which thankfully I can do. So pi over 3, I'm going to go out 1.5, so 1, 0.2, 0.4, 0.5. So far so good? And then finally at pi over 2, we of course don't want to go anywhere. We want to be 0. So pi over 2, I'm at 0. Now notice something very strange about the origin then. I don't care which way I'm facing. If the next part is 0, I'm going to stay at the origin. So the origin is actually, can you tell what the angle is there? No, you can't tell at all what the hell the angle is. You can't even give me a reference angle. At least if I gave you this point, you could say the reference angle must have somehow been pi over 4. It must have been either, you know, some kind of negative over here, pi over 4 related deal or something. When I'm at 0, there's an infinite number of degrees it could have been. All right, and what's going to happen now as you move out of there? I'm going to repeat these values, aren't I? It's kind of nifty. What's going to happen when I get, so we've done this much. We've done this much here. Is that cool? We've done from 0 to pi over 2. So of course now I'm going to have all the same values. They're just going to be the negative. So that's kind of cool. So now instead of facing, I'm going to, if I want to go to pi over 3, it was 1.5. So now if I look at 2 pi over 3, let's see if you guys are still kind of with me. If I look at 2 pi over 3, what should my output be? Negative 1.5. Because I know I'm in this region. I know now I'm sort of like in the second quadrant if I want to think back to unit circle. So I know my x's are going to be negative. And we're dealing with cosine, so it's related to x's. So now at 2 pi over 3, I'm going to have to go back 1.5. So back 1, and here's my 2. So back 1.5 will be right there.
Which one?
As you can tell, it's definitely going to take some getting used to. So let me go through that again.
Yes.
So what does cosine do? It starts off big, and then it gets tiny. And then it grows again, but it grows negative at the same rate that it shrank. So it starts at 3 in this case, goes to 0 at 90 degrees at pi over 2. The minute I start going back, it's going to start to grow again, but it's going to grow negative. It's going to be the same values that it went through to get down to 0. Now it's going to increase back up to negative 3. It's going to be all the negative outputs. So I can just look back here and say, now I'm going to just go through this backwards. At the pi over 3 kind of reference angle, I should be at negative 1.5. So now I'm going to start to grow up to its minimum. It's negative 3. So at the pi over 4 reference angle, at 3 pi over 4, so if I face here, 3 pi over 4, which way should I go? Negative what? 2.1. You guys see where that came from? Maybe not on mine, but on your paper you should see it. So 3 pi over 4 is here. Go back. So here's the back part of it, negative 2.1. Alright. And then, incredibly enough, The next step I take, the pi over 6 related dude, I should go out negative 2, 6. So this guy here, I should go out back 2.6. And then finally, when I get to pi, I should go back 3, because that's going to be this here. When I get to pi, I should go back 3. So pi, I'm right back here again. Now what's going to happen then when you get into the third quadrant? What's going to happen? So here, let me kind of go through this with this. So the first quadrant outputs, and this is where, now I got to be careful when I say that, because I really want you guys to realize there is no first, second, third quadrant here. There isn't. I'm referencing back to the unit circle that we know, right? And the fact that we only did the XY table, the R theta table, we only did it for quadrant 1 values. Why? Because we know all the other ones then. Just throw the negatives on at the right time. So from 0 to pi over 2, it's all positive outputs. The cosine starts maximum and then shrinks to nothing at pi over 2. Then I want to turn to the 2 pi over 3. But the minute I'm in the second quadrant, cosine is negative, so we had to go back. And then again, turn to 3 pi over 4, go back. Turn to 5 pi over 6, go back. And then turn to pi, but cosine at pi is the biggest negative, so it's going to go back again. Now what's going to happen when I go into the third quadrant? Yeah, so I started maximum, went to 0, went through all my negatives, and now I've got to go through the negatives and decrease. Of course, at the same freaking rate again, with the same values. So now if I face here, at the pi over 6, sorry, I'm going to have to go back, and I'm going to be right on top of that same point again. So it's going to start tracing back over itself. It's going to start repeating itself right then. So what shape have we kind of made here? Yeah, we made a circle. A circle that's centered on what axis? If we think about this back as xy. Yeah, it's a circle centered on the x-axis, because what function shows up in my R equation? Cosine. So what if I would have put 3 sine theta? It would have been a circle centered on the y-axis. It would have been up here. Ooh. Right? So some of this, again, this kind of comes back to stuff that we know. It starts to make nice analogies. It makes some sense. And now I will warn you, as you're doing these problems, you're going to go a little bit crazy with what angle you're looking at. Am I moving back, forward? When does it start to repeat itself? You might start to realize that here. Because when it starts to repeat itself, just stop. Right? There's no need to go forward. Okay, that was a relatively simple equation. But that circle, what would the equation of that circle be in rectangular coordinates?
It's 1.5 square.
Pi?
Pi?
No. Come on now.
Is it x squared?
What's the equation of a circle in rectangular?
X squared plus y squared?
I like it. So that would be at the origin, right?
Yeah.
X squared plus y squared
3x.
equals r squared.
So with 1.5 squared.
Now tell me, what's the radius of this circle?
3.
1.5. Be careful, that's diameter.
Yeah, 1.5.
You guys with me? So I kind of know, and also how much, what's been moved? How much has it been moved in which direction? I almost gave it away there. 1.5. Yeah, 1.5 over here, right? So the center is at 1.5, 0, and the radius then is 1.5 because it actually touches the origin. Are we doing so far so good? Okay, so it would actually look like this. It's been shifted to the right by 3/2. And the radius is 3/2. So we know what the equation should look like. So let's actually try to start with this. Oh, and Angela, I totally forgot. I don't want to make you have to crouch around with this thing. So if I start with this equation, somebody help me out. I think this might actually be exactly one of the ones we did. Who remembers how do I convert that to rectangular? What's missing to help me convert this to rectangular coordinates? What is y in polar? So what's x? If y is r sine theta, x is r cosine theta, so what's missing here? An r, so how do I make an r show up? Put it there. No, yeah, multiply both sides by r. So if I multiply both sides by r, I get r squared. This you just told me is x. R squared is x squared plus y squared. Good old Pythagorean theorem. Of course it is. It's still here's r. So of course it's going to be x squared plus y squared equals r squared. You know, nothing major there. And what's this starting to look like? You work with this and you complete the square, it's going to be exactly this. Okay. Hopefully all just containing your excitement. All right. What's I'm sorry?
Where did you get the?
All right. Which part do you not get? I'm sorry.
Okay, there you go. Go again slowly.
All right. What's r squared in terms of x and y? X squared plus y squared. That's a known
okay.
thing. And what's r cosine theta? X. Just like r sine theta is y. Now if I do the completing the square work, let's see if you guys can put up with me for a second. Half of 3 is 3/2. Squared is 9/4, so don't you have to add 9/4 over there? Then this can be written as x minus 3/2 squared plus y squared equals 9/4. 9/4 is 3/2 freaking squared, right?
Right.
All right.
Oh.
So which formulation do you like better? Do you like that equation or do you like r equals 3 cosine theta? Now, of course, I know some of you guys are like, well, no, Jeff, I like that better because I know it better. But now you're starting to see that, of course, the equations for circles are going to be easy as hell in polar because polar is based on freaking circles. It should be easy. In fact, here's the easiest, beautiful little equation you've ever seen. And somebody tell me what it is. Here's an equation in polar coordinates, r equals 2. This might freak you out because what variable is missing? Theta. But what's got to be true? What's that equation say must be true? The radius must be 2. Yeah, so I'm going to start here and go out to 2. So any angle, no matter what the angle is, angle doesn't even show up. The radius must be 2. So I'm going to get a circle of radius 2. So if it's not been shifted, the formula for circles is stupid easy. Because what's the idea of a circle? The radius stays the same. That's exactly what that equation says. R equals 2. Radius stays the same. So that's ultimately easier to write an equation of a circle there if it's not been shifted. Even if it's been shifted, it doesn't even get that much more difficult. Okay, maybe. Okay.
Should be in the center here.
If it was this, yeah, it would be in the center. The center of that circle would be 0, 0.
It doesn't mean that any circle which has a radius of 2.
So I mean, why would we?
Not, it would mean any radius 2 circle that's at the origin there.
And the origin.
Yeah.
So we should add this.
Yeah. Just like this means r equals 3 cosine theta is a radius of,
3.
well, radius of
3 over
1.5.
Yeah, but there's shifting.
That's been shifted by 1.5. Yeah.
So pretty much x will equal to. I don't get it.
So if r is 2, in fact, here, I can play with some more of these. In fact, let me do this. How do you graph the line x equals 2 in rectangle? How do you graph the line x equals 2? Yeah, and so no matter what y is, x is 2. So x has to be 2 there, 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 there. No matter what y is, x is 2. All right, so how do you graph r equals 2 in polar? No matter what direction you're facing, you have to go out 2. So whatever I want to call 2, call that 2. So I have to go out 2 there, go out 2 there, 2 there, 2. So I'm going to end up with a circle. Almost, Jeff. I think I went over a few. Circle of radius 2. Okay. My artistic ability is not what's important here. Thank God. It's the idea. So I mean, that you can't make that any simpler at all. Let's do one more, and then we'll take a break.
Yes.
You're gonna give us another sheet?
No, unfortunately, I only brought one. So this one you're just gonna watch. Let me see which one I want to do. Oh, cool.
So for our four columns at home, do we have to print out our own sheet?
Say again, sorry.
For like when we're doing homework at home, do we have to print out our own sheet?
Oh, yeah.
Do one then?
Or buy it. They sell Polargraphic. Or print it out.
Do that.
Yeah, that's what I would say. Let's do this here. Two plus 2 cosine pin.
Is it like other graphs where you can worry about the 2 layers? Do everything else?
Sorry?
Like how it says 2 plus? Is it the same with other graphs where like you can work, like do that last and do everything else first?
No. How can I say this? Because for any theta, some of the thetas might make it negative. So technically, probably could, but I would argue against that. It doesn't really help you. It's better just to go ahead and figure out what the points are directly and then plot them. So on this one, let's see if you guys can help me. Oops. So let's do the first quadrant like we did last time, and then we'll try to apply that to the graph. So 0. See, I can't make this guy do what I want it to. Yeah, we'll look. 0, pi over 6, pi over 4, pi over 3, pi over 2. So those are the basic ones that you always want to do at least, are those. So at 0, what is the value of that function? Yeah, because at 0, cosine's 1, 2 plus 2, 4, 11. How about pi over 6? A pi over 6 cosine is what? Root 3 over 2. And twice root 3 over 2 is root 3. 2 plus root 3 is about 3.7. All right, how are we doing so far? So this should be nice. All you're doing is plugging values in, and you're using angles that you know the outcomes for anyway. So this should be relatively easy. Pi over 4 cosine is root 2 over 2 times 2 is root 2. So 2 plus root 2 is 3.4, roughly. Pi over 3 is
Plus 1.
yeah, 1/2 times 2 is 1, so 2 plus 1, so it's 3. And a pi over 2
It's 2.
is 2. Now, the reason that we actually want to go a little further, contrary to what I just said, is what's going to happen with this one. Anytime you have an addition on top of your trig function, like 2 plus or cosine minus 3 or something, wherever your negative outputs, you're going to get smaller. Wherever your positive outputs, is going to make it bigger. Right? Because it's 2 plus positive versus 2 minus that same value. So you guys are semi-with me here. So if we start to build up again, we want to go to 2 pi over 3, 3 pi over 4, 5 pi over 6, and pi. So what is it at 2 pi over 3? And it's really the same idea as before. Cosine of 60. Why did I say 2 pi over 3? Yeah, that's good. Cosine of 60 is yeah, 1/2, right? So I got to start building up again. And 1, and it's got to be negative now, so it's going to be 2 plus 2 times negative 1/2. You guys kind of with me here? So 2 minus 1, 1. Yes, sir.
So you stop putting values when r equals 0?
When you hit all the possible values, when it's going to start repeating itself. Or here the problem is I haven't hit all possible values yet. I started at 4 and it went to 2. One more step is going to be 1. I haven't seen that yet. Shit, I better keep going. Because I haven't done all the ones where cosine is negative. Before I didn't have to do that. Why? Because there was no 2 plus. The output was going to be the same value, just negative. So I didn't have to write that down for myself. I just knew it. So just to be on the safe side, you might want to do a few and see if it starts to repeat or not. What about 3 pi over 4? Cosine of that's going to be negative what it would be at pi over 4.
Negative 2.
Negative root 2 over 2. So you get 2 minus root 2, which is like 0.6. Yeah. How are we doing so far? Alright. You guys look about like I thought you might. So the next step, the 30-degree angle, it's going to be negative what it is at 30, which of course is 3 over 2. So it's 2 minus root 3, which will be about 0.3 or so. 0.2? I think it rounds to 0.2. Can't remember. I know there's 1.7 something. So 0.2 something. And then of course at pi, what's going to happen? At pi now, cosine is negative 1, so you get 0. So after that, what's going to start happening after that? Now it's going to start to kind of build back up again. Go back, build back up in the sense that it's going to be less negative here for cosine. Cosine's going to get less and less negative. These values are going to build back through these. So that's what you want to pay attention to when you're making this. When does it start kind of repeating itself or start kind of growing back through this so I don't have to do any more work like this. I don't have to make any more table values. So now let's try to plot these. I guess you guys get to watch. Probably should point this dude at the action. That's good enough. So here's my table of values. At 0, let's set up a scale first. Let me see if I can set my scale smart here. 1, 2, 3, 4. Do I have enough room for 5? 1, 2, 3, 4, 2. 1, 2, 3, 4, 3. Looks like no. So I'll go with 4. 1, 2, 3, 4 is 1. 1, 2, 3, 4 is 2. 1, 2, 3, 4 is 3. 1, 2, 3, 4 is 4. All right, that was exciting. So at 0, I want to go out to 4. Then at pi over 6, I want to go to 3.7. So here's 3.7. It'll be a little bit more than halfway. Then at pi over 4, I want to go to 3.4. So at pi over 4, I want to go to 3, and it'll be a little bit less than halfway. And then at pi over 3, I want to go to 3. So that's nice. So at pi over 3, I want to go exactly 3. Okay, so let me stop there for a second. So this just takes getting used to. I mean, the first few points are pretty easy, but when you start doing negative, start kind of like going backwards, or you start repeating yourself, or you start, that's where it gets more interesting. Pi over 2, it's 2. So at pi over 2, I want to go up to 2, right there. And then 2 pi over 3, it's 1. 1 is right here. 3 pi over 4, it's 0.6. So 0.6 would be about right there, maybe. 5 pi over 6, we got 0.2. So it's going to be about right there. And then a pi, it's 0. So it's interesting. Right now we've got this much going on. We've got this here. Bam. It's neat. Now what it's going to do on the bottom is it's going to start to grow again, right? It's going to start to go back through these. Because what's cosine going to do? It's going to start to go back through these. Right now it's at its most negative. So it's going to go less and less negative. So the outputs are going to go through these again. So it's going to be this. It's going to be like a mirror image of this. So at so let me put these down here. So this is 7 pi over 6. Oh, you can do it, Jeff. Let's see, 11, 12, 13, 14, 15, 16 would be 8 pi over 3. Is that right? Yep. No. 16 over 12, so that would be 4 pi over 3, thank you. Alright. And of course, where's pi over, oh, here's pi over 4. 11, 12, 13, 14, 15, 16. Yeah, this is going to be, trying to see this is not, it's weird. Alright, this is going to be, you can do it, Jeff. 5 pi over 4, yeah. So at 7 pi over 6, it's going to start to grow again. It's going to be back out here just a little bit. 5 pi over 4, it's going to be there. So it's going to repeat these values again as you go back through. So at the pi over 3 reference is going to be here. And at pi over 2, it's going to be, here's 3 pi over 2, it's going to be back to this one. It's going to repeat that output again. Let me just stop right there. So at pi over 2, what happened? We went up to 2. You with me? At pi over 2, the output was 2. And then we got smaller and smaller and smaller outputs, didn't we? Now what's going to happen to cosine? Here's the cosine piece, right? All those interior things are what cosine is. As I move away from pi, what's going to happen to cosine is going to be less and less negative. So the outputs are going to go right back through the same values they just went through, just in the reverse order. So it's going to grow from 0 back to 0.2, back to 0.6, back to 1, back to 2 finally. So why is this 2 on that side and this 2 on that side? Well, because here I'm facing pi over 2 and I go out 2. Here I'm facing 3 pi over 2 and I go out 2. Neither one of those was a negative output, right? All the r's here are positive. So I don't go backwards anytime. And then what's it going to be over here? It's going to grow again. So it's going to be mirror image. At the pi over 3 reference, it's going to be, where was I? Yeah, 3. So there's a mirror image there. And then at the pi over 4, it's going to be just a bit over 3. And then the pi over 6 is going to be just a bit over, right in the middle of 3 and 4. And then finally it's going to be back at 4. So it's going to come back out. Now the name of this is kind of nifty. I'll get 2 different answers for this, but what does that look like? A heart? Good. I'm glad I got that. Good. Yeah, that's a heart there.
It just doesn't have the pokey thing.
Doesn't have what now? The pointy thing?
Yeah, the
Well, this is slightly more correct. I don't want a pointy heart. That would be rough. So this is called a cardioid. Cardioid. Not party boy. No, that's somebody's Yahoo username. I don't know. Okay, so obviously this takes a little bit of work. Part of it should be very simple. You're just plugging values in. And what values are you plugging in? Stuff that you should know. Stuff you know the outputs for. So the first new thing is, how far do you take this before you can just